Can anybody see my screen?
Yes, we can see.
You should be able to see the slides, right? The slides for this
Yes.
week.
Yes.
Yes. Okay. Yeah. So this week we have been introduced to bag of words and the very simple multi-layer perceptron. And I think the fair thing about this week is that a big part of the lectures was them introducing the class format. So I think that will have helped us to get through things clearly. So here's the way that I want things to work. We are going to, I'm going to scroll through the slides, and then as we go on, I want people to maybe Shamsuddin can modulate. I want people to, show your hand if you like to contribute something to the conversation. Maybe something that you discovered while in that part of the video or the slides, or maybe like a question that you have that you want to get, explanation on or like further insight upon. And of course, if you have any resources, please feel free to share it in the chat. So Shamsuddin will be modulating while I scroll through the slides. So yeah. So the first thing they presented is language is hard. Working with language is hard, and I think we had they listed a number of reasons why working with language is while working language is hard, and I think there's about 5 of them. There's so many things you need to take into consideration. There's grammatical rules, which of course will vary from language to language. But even within one language, we find that grammatical rules can be very complex, and there are always exceptions. There are morphological rules, of course, and there are exceptions. There's semantics, which you have to put into consideration. There's pragmatics. There's that tension between semantics and pragmatics. That's what things might mean on the surface, given the words that you have, but so like what they actually mean because of the way that we say them, or like the context that we say them. I think that's where things like sarcasm come into play, in which they alter the meaning that of whatever it is that we say in language. And so because of like these types of things, we find that working with language is not it's not easy. So we have a couple of examples of this, and I found this discussion really, really interesting. If we also the videos, especially for, especially for the last 3, and the way they pointed out, for example, Jane go to the store. It's really an oversimplification of a grammatical rule, the way that we conjugate, the past tense of a verb. And then the store went to Jane, which in modern day interpretation, maybe will not sound so wrong, because of course, like the example they showed next, food trucks is an example of a store, which can of course go to a person. And then I think they went on to, despite like all the troubles we have with language, how can we design engineering solutions for language? And they mentioned talking about you create a set of grammatical rules. You could create a set of, and that could help you handle these ones where they are light. That's store to Jane when D and Jane when store. These ones, they obviously violate grammatical rules of English, so they're easy to spot and say, what, like this is incorrect, we shouldn't be doing this. And then for the next one, talk about using morphological exceptions, morphological rules. We know that the verb go is not conjugated this way in the past tense, it's conjugated with went. And for the next one, we have semantic categories and preferences. I think this is where they mentioned, should I say, actions that some nouns can take on and cannot take on. In the traditional sense, we don't expect that a store is something that that can go somewhere of its own. But in the modern sense, we do understand that some types of stores have that mobility. So like an understanding of semantic categories can help us also to handle, sentences like this. But yes, they did show that it's not just pertaining to English. We can do this in other languages and see that we still have the same issues that we have to find ways to handle. So yeah. So broadly, there's about 6 things to consider working with language. We have morphology, we have syntax, semantics or word knowledge, discourse, pragmatics, and linguality. I think I'm getting tired of hearing my own voice. So so far, can somebody share what they've learned, what they learned at least up to this point when they went through the slides on their own and the videos? Let me check the chat.
Hey, hey, Akintunde.
Hi, hello.
Hey, I didn't get a chance to go over the material for this week, but I did have a question about the slide that you just presented about the engineering solutions.
Okay, let me just go back there. Here we are.
So for semantics and world knowledge, how would that be a engineering solution? Because in my mind, that mostly happens with like having an understanding of culture. So a person would know logically a food truck can go to Jane, but a store can't go to Jane. How would we teach that to a model?
Okay. Let me think about that. I don't think I have an answer. That's an interesting question. Is there anybody else who had this question or maybe perhaps found an answer to that? I know that it's something that, as a human, if you tell me, I know that based on my world knowledge, I can tell. But, is there any way we can teach the same thing by creating sort of rules? Does anybody have an answer?
Hi. So how I understood it by engineering solutions was that it's like manually typing out solutions to deal with the problem. So you can replace not actual engineer like an engineer, but like creating solutions to solve the problem. So to solve the problem of the second sentence and the third sentence, we could create a grammar of the language. And then the following one would be the following sentence after that is considering morphology, whatever, and exceptions, and blah, blah, blah. So it's actually like typing out rules to solve the problems at hand. That's how I understood the slide when the guy was going through it. Yeah.
I think that sort of explains why they mentioned that this type of solutions are limited, because there's so much world knowledge that you cannot try to hard code, because in this case you simply have to hard code what types of nouns are mobile and what types are not mobile. But like there's a lot of actions for which you can spend time listing what nouns can do them and what nouns can't. So I think this type of solution really is limited in how much you can apply it. And I think that points to why in the later part of the course, we go to discussing neural nets, which can help us achieve some of these things.
Thank you. That was a great answer. Thanks both of you.
Hi, can I contribute something?
Okay, sure.
Okay, I quite agree with what Manuela said. Sorry if I'm not pronouncing your name correctly. And I also want to agree with what Vishaka posted in the chat. Like when the model tends to see you typing the right thing all the time, like it appears in the corpus, then the system tends to learn the right thing. If you look at it from the point of like question answering task, where a model was pre-trained on like an external knowledge source like Wikipedia that has the right form of conjugation. So every time the model is exposed to such corpus, then it tends to give the right answer in the right using the right verb and the right morphology. Like for machine reading task where the answer is a span of a particular text or a particular length, such will definitely pick the right answer from that knowledge source, which was actually which actually have a corpus that contains the right verb and the right noun. Yeah, so I want to agree with those two pointers.
All right.
And that's like the application I can give in question answering task.
All right. So, all right. Thank you, Tunde, for contributing. So I think we all agree that, this set of tools that we can create manually they're limited, and, they're very manual. They require too much work, especially if we are working with very large data. So, we get to talking about neural nets for natural language processing. And, we find out that they allow us to learn all of these rules and exceptions that we would manually have had to create. And, I think that's awesome. I'm going to skip this class format part, which is good for us, and get to, neural network themselves. And then, yeah. So, this, for the neural network section, I think they motivated by showing how you might try to classify sentences into 1 of 5 labels. Very good, up to very bad. You want to pick exactly one. And then, we're going to talk about how you might approach this. And then I think the first approach they talked about is bag of words. And then, yeah, so let's have somebody talk about what they had going through bag of words. Can somebody please share?
Okay. All right, let me jump in. So basically, in language processing, natural language processing, we need to create vectors derived from textual data, because we cannot actually use the textual data to manipulate them. So we need to create the vector that represent those data. And this kind of creation of vectors that represent the textual data is called feature extraction or feature encoding. So before you do any tasks in NLP, those texts need to be encoded into numerical representation. So old-time NLP, one of the first approach that is used, one of the first feature extraction of text is called bag of words or bag of word model of text, which is basically extracting features from the text for use in modeling, such as machine learning algorithm, because machine learning algorithm cannot use text. So bag of word is basically feature extraction from that text and represent it in form of vector.
All right, so thank you, Shamsuddin. But also in the video, if you all went through it and if you all remember, I think one issue that they mentioned with bag of words is that it ignores syntax. Because when you do bag of words, you essentially just break up a sentence into its component words and put them in a sort of bag, and then you assign a score to each of the words in this bag. We can say hi is sort of neutral. We can say don't, maybe that's bad, sort of. We can say love, oh, that's very good. And then because we ignore syntax, it's an issue. And I think one example that they use is these two, in which we have I don't love this movie, and this is say this is bad, but then we could go something like there's nothing I don't love about this movie, and this is very good. And the reason it's very good is because of the way the syntax is constructed, in which there's nothing I don't love. There's nothing I don't love. It sort of inverts what you might say about I don't love this movie, and that's one issue that that we find that bag of words might have trouble addressing. And then they speak about combination features, in which I think at first they speak about it manually, in which you try and introduce features that try and capture this type of combinations that might alter the sentiment of a sentence, like things like don't love and don't I love nothing. And then they speak about how this might be manual, and a better way to do it might be to extend your neural network to be able to learn combination features. And I think that's where they begin to introduce the continuous bag of words. And
Sorry, I have a question.
Okay, please ask.
Okay, so I mean, I can understand bag of words
Okay.
ignoring semantics,
Okay.
but how does bag of word ignore syntax instead of semantics? Because what just looks like sound like semantics.
All right. So sorry, I'm not the linguist. So if I mix this term up, please do correct me. And so I want to say essentially that a bag of words does not care about the order of words.
That's the semantics, not syntax.
Okay. So it doesn't care about it doesn't care about the order of words. It's just what words are in the sentence. It really doesn't matter the order in which they occur, or the way that they are arranged to convey meaning. It's really all about what words are there, and then what are the sentiments we attach to each one of these words, and then we can sum up that sentiment and have a score for the entire sentence.
What do you said first that he corrects you? You said they don't follow what?
I said they ignore syntax, but he corrected me that I said semantics.
Okay. So when they discard because they don't follow the order of they ignore order of word within the context, right? And that if they ignore the context, then they basically ignore the semantics, right?
Yeah, I think that's what he's trying to correct me about.
Okay, yeah.
Okay. Yeah, so we mentioned combination features, and then, we said, if you could extend your neural network with some complicated function to extract these combination features, then you could get a score for the same sentence, and then we would have a sentiment accurately for it. And then also, motivated by, please speak.
Yeah, just the previous slides.
Okay. Yeah. So
you made one of disadvantage of bag of word is they ignore drop semantics. So another disadvantage of bag of word is like sparsity. So when creating bag of word, this is one of the problem of bag of word, and it is computationally expensive to do calculation with sparsity. Yeah, I think also this is one of the issue that leads to the drop of bag of word. I don't know if how they generate sparsity.
All right. So what I would like us to do really is to go through each of these three techniques that they introduce. Talk about the bag of words and talk about the issues that they have, then go on to continuous bag of words and the issue that they have, and then deep continuous bag of words, the issue that they have. And then after that, I would like us to spend maybe the last 20 minutes walking through a code example, which I will share soon. So I'm putting this ahead here so we know that because we have a lot of slides, we might not go through every page of the slide. But if you do have any question on any page that we skip through, please ensure that you raise it in the chat chat, so that everybody can contribute, maybe answer your question. So yeah,
I have a question.
Oh yes, please go on.
Yeah, so what does it mean to represent a word as a vector? Like, how would you do that?
All right. Yeah. So let me defer your question until we are doing the code walkthrough. It will be better for me to be able to show you exactly how we might represent a word as a vector, or a sentence as a vector. Is that okay?
Yeah. Thank you.
All right. Thank you. So Shamsuddin mentioned sparsity, which can become a problem when we are working with bag of words. And that is something that we might be able to demonstrate while doing our code walkthrough. So let's keep that in mind. So for now, we've mentioned that if we could find a complicated function to extract combination features, then we might be able to improve, our classification of sentences by their sentiment. And then based on that, we introduce a continuous bag of words. And all right, can we have somebody share what they learned or a question that they had about continuous bag of words?
So Tunde, they are moving slowly from bag of word, moving toward neural net, right? From the previous, can you go back a little bit to the previous slide? Yeah, so here, So here they are thinking, okay, now here we just use feature extraction to just encode the text into some vector representation, numerical. but they are saying, okay, now how can we automatically extract these features, combination of features? So this telling us that neural net can magically extract these features automatically. Am I right?
Yes. So one of the things you learn about neural network, I think they mentioned it in this week, is that the neural network is essentially a universal approximator, and that theoretically, there's no function that it cannot approximate. So if there is a function that can extract any of these combination features, then your neural network definitely can extract those features.
Okay, good. Thanks.
All right. Yeah. So we go on to continuous bag of words. And the key difference that we have between bag of words and continuous bag of words is that whereas in bag of words, we had, if I go back to the diagram, just so everybody can look at it. If you remember, we had individual words. We did a lookup and then got scores for each one of them. Then we added a bias, and then we had, our final prediction for the sentence, the sentiment of it. When we are working with continuous bag of words, a key difference that we have is that we no longer just get the scores for each one of the sentences. In effect, what we get is a sort of representation of the sentence across chosen dimensions. In the code example we'll look through, if I remember correctly, the dimension they chose was 5. And then we have representation across those 5 dimensions for each of these words. Then we do a linear combination, using, we have a weight matrix that will multiply that by, then we had the bias before we then get our eventual score. So what is happening here is that rather than just getting individual scores for each of these words and then summing it up, in our case, we introduce a way, which is weight matrix, which can sort of combine, let me say, the features of individual words across different dimensions. And I think that's what really helps to capture the combination features that they mentioned here, if everybody gets that. So it's this extra step that is really helping to extract those combination features that then improves the predictive power of the continuous bag of words. Does anybody have any addition or a question?
Tunde, how do you define this weight vector? Is it arbitrarily or how?
How do I define what?
The weight vector here.
Yes. When I say better, you mean when I said continuous bag of words was better than?
No. I'm asking here. Here, so we have weight vector. Is it a vector,
okay.
right? So
yes.
How do you define this weight vector? Is it arbitrarily we define it?
Okay. Okay.
Or we initialize it in some ways?
Oh, okay. I think that in this particular lecture, they go through the basics of a neural network, and after they mention about the way, let me just give context to my answer. We have a neural network, and they talk about the way that we define a computation graph. We define layer by layer, each layer feeding into the next layer. That's a simple neural network anyway. There are much more complex ones. And then we define a forward propagation in which you're passing inputs from the lowest layer and then feed it up to the last layer. And then we discuss, and then they mentioned backward, the backward propagation in which you have a final layer who is then, in which you take a, what do I call it? How do I explain it? In which you compute a derivative with respect to layers previous to it. And they mentioned that as you do that, you begin to update the parameters of the weights in your neural network. So what the model is doing in that sense is learning. So it's during that process of learning is when this particular weight matrix is shall I say I don't want to say created, but that's when it's learned to what it should be. So in the beginning, I will show you also when we start our code example, you will find that they choose an initialization scheme for our weight matrix, right? But over time, as the model learns, that's as forward propagation goes on, and then backward propagation goes on, and then parameter updates goes on, what do I call it? Sorry. The weights of this particular matrix is going to change over time to what's going to be the optimum matrix to extract the combination features that we require. So it's not that we have to have a weight matrix somewhere that we are sure works. It's that the neural network over time can learn what is the best weight matrix to extract combination features. Did that help, Shamsuddin?
Yes.
So
Somebody says they have a question. Can they please contribute?
Yeah, I have a question. So, you said that the main difference between a bag of words and the continuous bag of words is that
Yeah.
the continuous bag of words is a representation across a certain dimension. I'm
Yeah.
not really clear on what those dimensions are. Are they combinations of different words in the sentence?
Okay. I think it's time. Let me switch to the code example. Then I think like we'll start to see the differences that we have between this between bag of words and continuous bag of words. Is everybody in agreement?
Yeah.
okay, so I think to answer that, so the dimensions of your weight are basically the so you have the size of your vocabulary, right? So if let's say for example we have the size of this vocabulary is 5, we have like 5 words. So the dimension of the weight would just be the length of each vector, right? So in this case, the dimension of this weight would be like 4 by 5. Yeah.
All right. Thank you for contributing, Charles. All right. So give me a moment to switch.
I'm sorry, 4 by 4. Yeah, because it's 4 words by 4 dimensions. 4 by 4.
Share screen. I'm just going to share my VS Code. I took the liberty of walking through the code example for the week. Please let me know once you can see my VS Code. Can everybody see my VS Code?
Yes. Yes.
Yes.
Okay. Yeah. So I'm going to first start by showing the data we're going to be working with. And we're going to have it here. And if you can see, the first thing we have in our data is a tag. And then we have a separator. And then we have a sentence. And that goes on throughout. We have a number of examples. It's a sizable number, maybe about 10,000 or so of them. And then the first thing we're going to do is to read in this data. And, they have a neat little function that does this. And I think I struggled in the beginning to understand this default dict that they did here. It's a smart little trick that simply maps, Well, let me start by reading in this thing. Okay, let me start. So we have, just reset because I had run this code previously. Just do the usual inputs. And then I'm going to say, for now, I'm just going to open it like this and then I'm going to say comma R. Oh, sorry. It should be like this. And then I'm just going to read one line. Yeah. So you can see we have the first line in the sentence, and as usual, you can see what I said. We have a tag, we have a separator, and then we have the actual sentence. So what's happening here? We have the read data set function in which they read line by line. They take the sentence and then they lower it. If we call lower on this sentence, for example, you see that everybody switches to lowercase. And this is one thing I would always do especially if you are new to Python, is to try and break down codes slowly so you can understand exactly what is going on. Next is strip it. So if you call strip on this, we see that any empty space at the beginning and end of the sentence should disappear. And then after that, then they split the sentence. So they split it using the separator. And in this case, the separator is this, these 3 lines that we have here. So I'm just going to copy it and then paste it, and we see that. So now we have a neat little list in which we have the tag first, and then we have the sentence itself, right? And then once you do that, the next thing that they do is to, what do I call it? In essence, they yield a list of, let me do it this way to simplify it. I'm sorry. So try and follow me as I go on. I want you to just know that a default dict is a dictionary that defines, shall I say, a default for its keys, a default value for its keys. So in this particular case, they've defined default value for this particular dictionary to be equal to the length of the dictionary at that particular point. And now, as you might expect, we are going to add, as you add new keys to your dictionary, the length of your dictionary definitely is increasing, right? So what this is doing in a very neat way is that it's assigning each word to, what do I call it? To a unique index. So say, for example, I pass in you, and then I could say, you see that we have 0 because, our dictionary was empty before. But, if I go on to, if I add a new word like your, now I should get 1. So if you can understand what's going on, because of this neat little function that is mapping each word to the length of the dictionary, it's in effect assigning each word that that is passing to dictionary to a unique index. And you can confirm that this index is unique by passing in a word we've passed in before, like you. And if you pass it in, you see that we still have 0. It doesn't increase to 2 because, the dictionary had seen the value, had seen the word you before. So let me just clean this up and then we can go back to the function. So now we understand that these 2 dictionaries are just to map words and tags to their to unique indexes. And then we include an unknown function, an unknown tag unknown word, just to represent words that we do not know. And then from there, we're reading each line in the sentence. We've shown that this splits it into a list that contains the tag and then that contains the sentence. And then from there, we just use the list of the word vector and then its tag. So this should answer a question that was raised about how do you represent a sentence or a word as a vector. So this is one example that we're going to see here. So let me start here and then let's read in the data set and see what we have. So I'm going to just read it in and then now we have train. So if I call type train, we'll see that train is a list. And if I call len train, we see that there's about 8,544 values in train, which corresponds to like the length of the data set that we read in. That's train.txt, which I showed before. Then we can index train and look at what is at position 0. That's the first element. And what we see is that we have a long list of words represented as numbers. So each of these is a word that's represented by a number. And at the end of it, we have an index. So if I only wanted to show the sentence, I could index it and call 0 again. And this time we would have this guy. So this is in effect the first sentence in our, what do you call it? The first sentence in our data set. And I can, let me bring up sentence again so we can see it. So I think I did something like this. And then I said, let's open up this guy. Comma R. And then I called, let's read the first line, f.read line. Yeah. So this is the first, this guy. This is the first sentence that we encounter. And you can see how it's represented as unique numbers. And so you can see that we have each of the words in this particular sentence is mapped to a unique number. And for example, you can see that 9 is repeated twice. And I think that's because the word at position 9 occurs 1, 2, 3, 4, 5, 6, 7, 8, 9. Which one is it? It occurs somewhere again. I can see it. But yeah, so using a function, you can map each word to a unique index, and then you can simply go through each sentence. You can go through the sentence, and then for each word, just replace it by the index, in your dictionary, and then you would have a vector that represents your. Oh, there's a lot of. on the chats. Oh, I think those are getting answers already. Yeah. No, so 3 is not a sentence number. 3 is a tag, which in this case, I think refers to a sentiment, which we are trying to classify as in this case. So far, does everybody understand up to here what we've done? We've been able to read in data set. We've been able to split it into sentences and then the tags. And we've been able to represent our sentences as a list, as a vector, in which each word is represented by a unique index, which we calculated. Yeah. So let's revisit our first example. We are going to look at a bag of words and add bag of words. And in this case, we are using PyTorch. And of course, this can be done in like any of the other libraries. You can do it in TensorFlow also if you want to. And so yeah, so let's run through it simply. When you're building a model in PyTorch, all models should subclass touch.nn.module. And then you can define, what does my model need to initialize? And in this case, it's number of words and then the number of tags. So that is defined there. And then from there, we define the bias vector. For now, the bias vector is set to zeros of length, number of tags. And then we define an embedding vector. We define an embedding layer. And then, sorry, I wish I could share like 2 screens at once. It would have been nice to be able to show the representation of, give me a moment, please. I just want to get, if we can refer to the diagram that was drawn for bag of words, we see that for each of the words that you add, there was a way that they were able to extract a score for it. And then those scores were added to bias. So in this case, the embedding layer is what is supposed to extract the scores for each of the individual words. Does everybody get that? Yeah. So we have an embedding layer, and then I think Charles mentioned it before. He spoke about dimensions of he spoke about dimensions that we might have. And in this case, our embedding layer has dimension, number of words by number of tags. In this case, I think we have 5 tags, if I'm correct, corresponding to very bad, very, very bad, bad, neutral, good, and then very good. And then so we have an embedding layer that has dimension, number of words by number of tags. And then we have this way you see the initialization is occurring, which I mentioned before. So at the beginning, when you're creating your neural network, you can decide to initialize. You decide the way that you can decide the way that it's initialized. So in this case, they're using an Xavier uniform initialization method. But like I mentioned before, as the model passes over data set and learns, what you will find is that the weights that have been initialized will be updated to, shall I say, their optimum values, sort of, if you understand. And then, and I talked about the way that a neural network might learn by a forward pass over a data set. And then, we define the way that forward pass works. So in our case, you pass in a vector of words, and the vector of words is immediately passed to your embedding layer. And at this stage, from there, we take a sum, which is something we mentioned before, that for bag of words, you immediately take a sum of the scores that are outputted across each word. So we take a sum of the output of the embedding layer, and then we add the bias. So give me a moment. I want to stop sharing and then go back to our slides. And then let me share the slides once again. Share screen. Oh, let me just share desktop one.
So I have a question.
Yes, please ask your question.
So the question is on the code you shared. You said the embeddings are used to extract the scores. Do you mean in this particular example, or you mean generally?
No, in this particular example, there's a variety of ways that you can employ your embedding layer, which even in this particular like in this particular lecture, we might find out. Because if you go on to the continuous bag of words, they also use the embedding layer, but they are no longer extracting scores. In that particular case, they're extracting representations that you then use, if you understand.
Okay.
I wanted to refer to this diagram that we have here. So in this case, we have I hate this movie, right? Our embedding layer is acting as a sort of lookup that then outputs the scores, which are then summed up and then added to the bias. to get, the final score. Does everybody understand that? So if you refer to the code also, you can see that we employ our embedding layer for the vector of words, then we take a sum of all of them, and then we add the bias to it. Does everybody see that? And then that's the bag of words. So if I run this now, for example, now I mentioned that when you're doing Shamsuddin, you're going to speak.
Hello, I can do it.
Yes, please ask.
I'm sorry for cutting. Please, can you share a material because I'm new to Python sharing. I'm really lost.
Okay. I understand that. But let me ask and say that at the high level, do you understand what I'm explaining?
I'm lost actually from the beginning of the class, from the initialization of the class.
From the initialization of the weights, right? All right. Let me do a simple example that might help you. It will not get you, of course, fully up to speed. But it might help you just visualize what is happening. So let me do something like I'm going to call nn dot embedding, and then I'm going to say we have 10. I'm going to say we have 5, right? So let's just call it like that, and then we can do something like this and call the weight. Yeah. So what you see here is so I've initialized a simple embedding layer that takes about dimensions 10 by 5. And then you can see that our embedding layer has been initialized by itself. Usually when you create a layer, it's automatically initialized. Its weights are automatically initialized. Of course, you can decide how you want to initialize it, like we did here. But generally, if you do not initialize it, Python will do that for you. So that's what has occurred here, if you understand. So now I can do something like I can pass a vector, for example, into this embedding layer. Like say I could do let me do something like search dot tensor. Let me say 4, 5, 6, and then all right, this should be it. And then yeah, so this is what has happened. Let me pass it and say we have emb.weight. So these were the weights of the initial embedded layer that I created, right? And then this I passed in a vector of words. Now you can see that what happens is that for each of I passed in a vector, right? Just assume that. Sorry?
I said I was thinking you need to rerun that cell.
No, I will not need to. I just retrieved its weight. So if you can see now, what happens is that I have passed in a vector that has 3 items, and I want you to know that each of these items are words. And you can see that what has happened is that there's been a sort of retrieval, right? Remember we said that I mentioned that our embedding layer is acting as a sort of lookup, right? So I want you to look at my weight matrix and I want you to count up to position 4. And remember that Python starts indexing at position 0. So this position 0, position 1, position 2, position 3, position 4. You can see that our embedded layer has been able to retrieve the matrix at position 4, and that's what's happening at position 1 here. Can you see it? Can you see?
Yeah, we can.
Yeah. So you can see what I mentioned about the embedded layer acting as sort of lookup. So when you pass it a vector representation of a sentence, for each of the words that are represented in that particular sentence as items of the vector, the embedded layer is able to return a representation of the entire sentence by looking up each one of the words. Maybe if I index this guy by 4, it should, yeah. So you see for 4, it indexes what is at position 4 of the embedding weight, and same thing for 5 and for 6. And then after you're done with that, what happens next is that we take a sum of let's assume, for example, like we have this guy here at cell number 24. And then from our bag of words, we said that after using the embedded layer to look up scores, we take a sum of all these guys and then add the bias to it, right? So we can come here now, for example, and take a sum and say touch.sum this guy, I want you to add it along dimension 0. And then, yeah. So you see what happens now. So we've started with a sentence, which was, our sentence was 4, 5, 6. We passed it through an embedding layer, and then we got a set of scores across 5 dimensions, 1, 2, 3, 4, 5. And then we summed those scores across those dimensions, and then we had our final value, which we then add a bias to, which is exactly the way that a bag of word occurs. So if you follow me once again, we use the embedding layers to do the lookup. We get an individual scores across 5 dimensions for each of the words. We take a sum across each of those dimensions, and then we add a bias to get our final score. Do you understand better at a high level now?
Yes, thank you very much.
All right. But I will share a resource with you at the end of this.
Expo want to talk.
So,
Okay.
if I'm not mistaken, and this embedding is just containing the score of each word in, the column of each vector is the score of each word for each sentiment.
Give me a moment. Let me do Control Z, and then
like in the embedding layer. Stop there.
Yeah.
Like the first
Yeah.
element is the score of this word in the. Let's say this is a positive sentiment, neutral.
Okay.
Is the score of the word in that class.
Okay, so let me do like this. Let me say, sorry. Okay. And so this is what we had before. Let me detach it and then call it numpy values, and then call numpy something like this. All right, give me a moment. I'm just going to import something just to make it simpler for you. Let me import pandas as PD. Just ignore all of this, and then I want to just Control C, Control V, and then I'm going to say something like, is that correct? I'm going to say columns is equals to, and I'm going to say very bad, bad,
Yes.
neutral, good, and then very good. Well, I hope this.
Sorry, quick one.
Yes, please. Go on.
So I'm trying to get an understanding of the question. So is he asking if the vector in the embedding is a sentiment?
Okay, so I think he's asking like, what do each of the dimensions in this vector represent?
Yep.
Yes.
Yep, that was my question actually.
Yeah.
And
so,
when you do like this, it makes more sense.
So I hope you understand now.
Yes, I understand.
All right. So what is happening is that we've taken, what our embedded layer does is that when we choose an embedded layer and then we chose its dimension to have 10 words by 10 by 5 as its dimension, it means that the words are projected to 5 dimensions. And in this case, dimensions we're interested in are very bad, neutral, good, and then very good, if you understand me.
Yep.
Okay. Sunday, sorry to cut you. So my understanding of embeddings, I assume that the length of the vector is an hyperparameter and does not necessarily refer to like classes and stuff. Because if you look at like the original Word2Vec paper, for instance, they suggest embedding length of around 250 to length 300.
Yeah. All right. So 2 things I'm going to say is that I'm doing this as a high level understanding to help them understand exactly what's going on here. And I think that's exactly why they chose 5 in the paper. In this particular lecture. The truth is that you could really choose more than 5 as the dimensions which are projecting like each individual word. So it's not a strict rule that when you're projecting like, it's not a strict rule that this dimension represents very bad, this dimension represents bad, this one represents neutral. But what I want you to understand is that the embedding layer takes each particular word and then projects into like dimensions that are able to show, should I say, the differences that exist between like each of these words. And then by understanding like the features that the embedded layer gives you, you can combine them to get exactly what you want. So like you mentioned in the what to vec paper, the dimension is an hyperparameter, right? You can go, you can take it as large as your computer allows you to, or as low as your computer allows you to. So when I do this, I want you to take it with levity, sort of, not with levity, sorry. What's the word I'm looking for? Take it loosely, just to help you understand. It doesn't necessarily mean that each of these dimensions represents very good, neutral, bad, or very bad, because we could actually have gone to our embedded layer and made it a 10x6 embedding layer and still been able to get our results. So thank you for contributing that. I think it's something important that everybody should note. But I hope that this gives you a better understanding of the way embedding layer is working. Is that it's taking your words and then it's projecting them into a dimension that allows you to combine their features. Does everybody understand that? There's silence. Should I take it as a yes? Is there any message on the chat? All right. All right. So there's two things to share now. Odun, can you please share the what to vec paper on embeddings? Share it in the chat, and so as a resource for people that want to understand better. So yeah. So the next thing is allowing our neural network to learn. And usually we do that first by defining a loss function. And in this case, we're using cross entropy loss. We also define an optimizer, and the optimizer will be in charge of working with our parameters and getting them to what you might say, their best possible values over the number of training steps that we take. All right, I can also clear this guy to simplify this. So we're going to run model. So now we've initialized our model, and I was going to run this just so we can see it. So we have number of words. We see that there are about 18,000 plus words here, and number of tags. We see that there's 5 tags here in this particular this thing we are working with. So now we have a simple training loop, and so we're going to train over 100 steps. We shuffle our train data. It's always good to shuffle your train data just so you don't have some bias that you learn. Like if, for example, all the positive sentiment ones came first before the negative sentiment ones, we want to shuffle it to ensure that we don't have stuff like that. And then if you remember in our train, I mentioned that we've separated our train 0. So our train is a list. It has a representation of the sentence, and then it has its tag. You can look at the sentence like this. This is representation of the sentence. Then you can look at its tag. You can see, what tag it has. So we say for each word and tag that we have in train, I want you to convert this word to a tensor, because if you remember, our word is a list of numbers. Convert it to a tensor. Our tag also is a single number. I want you to convert it to a tensor also. And then we pass, we pass the word, which is a vector, into our model. We get some scores. You can demonstrate that here by saying, let me say words is equals to touch.tensor, let me just say 456. And then I can do something like model, and then I'll just pass words, right? Yeah. So you see that we get, we get scores across 5 dimensions, right? So that's what's happening at that step. So we get the scores, and then when we get the scores, we take a loss function between the scores that we obtain and what is the actual tag for that particular sentence. When the loss is calculated, we add it to our, because at the beginning of our training, we set our loss to 0. We add it to our loss, and then we call the optimizer we zero the optimizer, which you always do before you perform your, then we do our backward propagation. Because if you remember, when I gave a high level of the way we train a neural network, I mentioned that we have a forward propagation, which is occurring here, in which we're passing, your words through your model. And then when you do that, this is run, it's passed through embedding, the sum is taken, and then it's returned. So after that, we do our backward propagation, which is occurring here, and then your optimizer takes its steps. So in this case, we're asking the model to train for about 100 epochs. Just add again here. And then we can Oh, I should probably have reduced it from 100 epochs anyway. But you know, it's just going to leave it and let it run. Yeah. So while that is running, I want to once again raise up something that I mentioned last week, which is that we are looking for people to volunteer to be anchors. If you're going to be an anchor, you're basically going to do, you know, exactly what I did today. You know, if you, which is you're going to be in charge of spurring conversation around the topic for the week. But also, you know, if there's any code, you know, for the week that we need to go through during this study, you don't have to be the one to go through it. If you feel like you're not confident, you can't handle that part, you can reach out to Shamsuddin or myself, and then we'll see what we can arrange. So your job really as an anchor is to stimulate conversation and get everybody talking about what they learned and what they had trouble learning about the course material for that particular week. So we are looking for people to volunteer to do this. Please, if you would like to volunteer once again, please just go to, everybody has a link to this, our page we are using. You can go here and then comment your name that you would like to volunteer for any of the weeks that we have ahead of us. And Shamsuddin or myself will reach out to you and help you plan towards your, is it Anchorage? So one of them. So please, we're begging you guys, please volunteer to Anchor. We will be on hand to support you in any and every way that you need. So our model should almost be done.
Sorry,
training.
I have a question on this. I don't know if there's still time.
Okay. You
okay.
Very...
Okay.
Yes.
Yeah. So from on this cell, yeah, you had scores, and scores is like a vector of 5 numbers, but you're computing the loss against a single value. So my question is, under the hood, or somehow are we using the argmax of the score, or what exactly?
Okay. So I think that's a very smart question. And your question has to do with in particular this cross entropy loss, which we are using, right? And I think the best way to understand really this type of things is to check the documentation and see that, you know, like, how does this work? And that is something that I had to do myself today when I was going through this code. You know, I had to go back and look at cross entropy loss and say, like, you know, how does this work? And I think I found a really interesting thread about it on discuss.pytorch. I'm not sure if I can find it anymore. I can't find it. I should probably have saved it when I found it today. But like, what I want you to understand about the cross entropy loss is that the cross entropy loss understands that the single value that is passed in is sort of the index of the dimension along which, should I say, the correct answer should be, if you understand.
Okay.
So let's say, for example, now if I you know, I have numbers, sorry, let me just call something, doesn't write random numbers here, sorry, just ignore them. They have no inherent meaning. I'm just using them to repeat. Yeah. So if you have, for example, this as what your model outputs as your scores, and then we go and say that our target is 2, right? Then cross entropy understands that we want this index 0, 1, 2 to be the one that is sort of our portion, should I say, the highest score. Do you understand?
Yes. That's what I said about argmax.
Yes, sort of. So yeah, so that's the way that it's working. So it allows you to pass in like a single number as your target, but so our model is done training now, and then we can check how it's performing, and maybe, so you can see we haven't using argmax here later on, and then so I'm going to simplify this just so we can look at something. I'm going to take the first sentence in dev. So this is what we have. We see that this is the representation of a sentence and this is its tag. So I'm going to retrieve its sentence and just say, I'm going to call it test sentence. is equals to dev, this guy. So now I can show you test sentence and see that this is what we have, right? So next thing I can do is that if I want to make a prediction here, I can say that scores is equals to, we take our model which we have trained, and then I pass in my test sentence. Let me just do like this. I didn't convert it to, sorry. I should have done like this. It should be a list. So our model is expecting a tensor, but I passed it a list. So we have an error there. So I'm just trying to correct it now. All right. So now we have it. So now I can pass in. Yeah. So this is what our model gives us. So I can take out the tensor, and then I can call it numpy. So I've converted now to a numpy array, still the same tensor as before. And then I can try and see, what was the highest score. We said the highest score was at position 0. And what we find is that in this case, the model was wrong, because if we check the tag that came with our particular sentence, the tag should have been 2 instead of 0. So like our model is not very correct. But I think what it helps us is to build an intuition around the way that we can employ bag of words to classify sentence into like 5 different sentiments. So you can run it over the entire data set, and we see that it's only correcting about 35.88% of the time, if you understand. So yeah, so that's it for this week. We've looked at bag of words. And one important thing to mention, wait, does everybody understand this so far? Any questions that come up again? Any addition? Okay, there's something in chat. Please speak, I can hear you.
So not so much of a question, right? But in practice, is there like a benchmark of how much bag of words compare with skipgram?
Compare with what?
Skipgram.
I'm not sure that I can answer that. Shamsuddin, or is there anybody else that can help? All right. Maybe it's something that we can note down and then ask me during the general meeting. But I think what I think here is that if I remember correctly, when with Gram, we are dealing with word embeddings generally. And in word embeddings generally, you want to create representations for like a series of words that you can then use for like downstream tasks. And which is like a little different from what we are doing here. Maybe sort of similar, but like not as involved. But I don't think I know about any benchmark. It's something that we can check for later on. Maybe if I find an answer, I can share it on the Discord.
Yeah, fair enough.
All right then. So
maybe I can say something on that.
All right.
So our model, which is called the bag of words, is not taking into consideration relationship between word. For example, if you keep the same slide, in this model, if we put the word movie and film, we will get different results. Like in this model, I had this movie and I had this film or this series. We'll get different results, but with skipgram or word embedding, I think movie, series, and film we'll get different results. And as you are saying, on word embeddings, there are two approaches. One which is conditional bag of word, and another one which is skipgram model. But I think that is we'll discuss about that directly in the upcoming session. There is a session on word representation.
Yeah, I think it's something we'll still encounter
Yes.
later on when we are dealing
Yep,
with
yep. Distributional semantics and word
semantics and-
representation.
yeah. So it's a question we can look forward to answering then. I'm just going to note it here in case it comes up. I'm just going to say compare skipgram and Sibal. So when we get there, we can try and find answers to your question. Is that okay?
And yeah, just for record,
I think
tentatively put me here for anchoring. Skip that one, just in case.
Sorry, I didn't hear what you said.
I was saying you can put me on anchoring that session if I'll still be around. Like
okay. Oh, okay. All right. I'm just going to note you down here then. And
yes,
I'll reach out to you. All right. Thank you very much. So you guys can also. All right. So I wanted to point out one thing.
I have something about the skipgram thing.
Oh, okay. Please contribute.
So I didn't really get the question, but I think, I mean, with regards to the response, I think what I'm about to say is kind of valid in a way. So you see what we've just done is like it's like the continuous bag of words. So skipgram is more like the opposite, where so you can see that in this case, the continuous bag of words were like using so we had a context like I love movies. I mean, I love this movie. We're trying to predict the the representation. I mean, the scores, for example. So skipgram would just be the opposite. Giving the scores, you're trying to predict the context.
All right. So yeah. So we still have we are way past our time. We don't want to take too much time. So I want to point out that we've only gone through BAO, which is bag of words currently. But also if you this week's topic introduces two other similar models that you can use to classify sentences. There's continuous bag of words, and then there is deep continuous bag of words. So I think one thing that we can do over the week is to try and go through either bag of words or continuous or sorry, either continuous bag of words or deep continuous bag of words that's on our own. You can you can follow the way the code has been written and then compare the performance to what we have with bag of words on the call today. And then maybe we'll learn one or two by delving into the code by ourselves individually. So I'm going to note that down also on the channel so we don't forget. So yeah, I think so far that's it. That's it for today. We're about 60 minutes over time. But everybody has stayed. Thank you very much for staying, even though we overstayed our time. Let me hand over to Shamsuddin now.
Thank you, Tunde. I think we are almost done. So as you explained, anybody that is willing to anchor the next session is we're happy to give you the session to anchor. So just reach out to Tunde or I so that you can have the record site. Thank you. All right.
So next week we are looking at language modeling and training tricks. There's videos and there's references. So same time again next week. And let's remember that if you have any questions during the week, you can always raise it up. You can raise it on the channel and somebody might have an answer for you. As you don't have to wait until we come on Mondays. You can engage during the week and see if somebody else can help you as they are going through their own studies also. So thank you all for joining today and for contributing.
Hello, can I just ask one more question before the session ends?
Yes, please go on.
So just for consistency's sake, are we going to be used, because I see on GitHub there's like a DINET approach and there's the PyTorch approach to the coding. So should we assume that we'll only be using PyTorch to answer the questions?
For me, I'd say that I'm more familiar with PyTorch. That's why
PyTorch.
I really went for PyTorch immediately. I saw there was an implementation.
Oh,
I
okay.
think, but like it's really about understanding the way that you can translate each of these concepts into code and then use them to achieve your objective. But I don't think there are many people that are very familiar with DyNet. I expect most people these days are familiar with either PyTorch or with TensorFlow or with JAX recently. So really, it doesn't matter. Just pick whichever you're most comfortable in with. Most people these days work with PyTorch or TensorFlow and just understand how you can translate these concepts into code. That's it.
All right, cool. Thank
Right.
you.
Anytime.
Thank you today.
All right, guys. So see you again next week.